exponential and logarithmic equations. Let's consider the following exponential equations. 5 to the x power equals 125, and 5 to the 2x power equals 5 to the x plus 1 power. When solving exponential equations, if we have a common base on both sides of the equation, these are actually pretty easy to solve. So for example, when we have 5 to the x equals 125, we need to know only that 125 is the same as 5 to the third power. And because now we have the same base on both sides, the only way that 5 to the x can equal 5 to the third power is if x is equal to 3. And this is because exponential functions are one-to-one functions. So this simply implies that x must be equal to 3. So please understand that we are not dividing by x on both, or dividing by 5 on both sides. We're not subtracting 5 from both sides. It's just that the only way this can be true is if these are equal. For the second part, we have 5 to the 2x power is equal to 5 to the x plus 1 power. Now, similarly, we have the same base on both sides. So the only way this can be true is if 2x is equal to x plus 1. So let's go ahead and write that down. And then to solve this, we basically have a very simple linear equation, and we can see that the solution is x equals 1. Now, these two examples are really simple, but I want to pose a different question. What if we had something like 3 to the x power is equal to 7 to the x minus 1 power? This would be quite a bit different, right? Because we don't have a common base on both sides. So how would we approach solving something like this? So we have some guidelines for solving exponential equations, and these guidelines would apply to exponential equations that are a little bit more complicated, like the one that I just mentioned. Basically, we want to isolate the exponential expression on one side of the equation, and then we're going to take the logarithm of each side of the equation and use the laws of logarithms to bring down the exponent. And finally, we solve for the variable. So let's consider the following example. So we have 3 to the x plus 2 is equal to 7. Now again, we do not have a common base on the left side and on the right side. So what I'm going to do is take a logarithm of both sides. And it does not matter what logarithm you use. So in this case, I'll choose to do a log base 10. So we have log of 3 to the x plus 2 is equal to log of 7. So we're taking the log of the same base of both sides. What this allows us to do now, using laws of exponents, is it allows us to bring down this power. So this becomes x plus 2 multiplied by the log of 3 is equal to the log of 7. Now from here, you can actually proceed in a couple of different ways. So one thing you could do here is just divide by the log of 3. And this would give you x plus 2 is equal to the log of 7 divided by the log of 3. And finally, we would subtract 2 from both sides, which would give us x is equal to log of 7 divided by log of 3, and then minus 2. And this would be our exact answer, and then we could plug that into a calculator for an approximate answer. And you can see here that the approximate answer for this, if we round to 4 decimal places, is negative 0.2288. Now there is another approach to solving the equation after this step. So let me take it from this step and show you what that would look like. So what we would do here, instead of dividing both sides by log of 3, is we can distribute here log of 3 times x and log of 3 times 2. Now that's going to give us x times the log of 3 plus 2 times the log of 3 is equal to the log of 7. And then we'll subtract 2 log of 3 from both sides. And that's going to give us x times the log of 3 is equal to the log of 7 minus 2 times the log of 3. And then finally, we'll divide by the log of 3. And we get x is equal to log of 7 minus 2 log of 3 divided by log of 3. And this is our exact answer. And again, we can approximate this by plugging it into a calculator. And once again, you can see the approximate answer here is negative 0.2288. Now, I know the first method might seem a little simpler and more straightforward, and I think that is true for this example, but there will be other problems where you will want to use these steps, and you will see those in just a minute. So in our next example, we want to solve the equation 8e to the 2x is equal to 20. So this is very similar to the problem that we just did, but there is one small difference here. So first of all, before we take a logarithm of both sides, we want to isolate this exponential expression. That means we want to get rid of the 8 here. So I'm just going to divide both sides by 8. And when we do that, we get e to the 2x is equal to 20 divided by 8, which is the same as 5 over 2. And you can write it like that, or you can write it as a decimal in this case. So you could just say 2.5. I prefer just to leave it 5 over 2. But the key difference between this example and the last example is now when we take the log of both sides of the equation, I do not want to use log base 10. And the reason is because there is a natural base of e in this problem. So I want to use a natural logarithm. So I'm going to take the natural log of the left side, and that's going to equal the natural log of the right side. And this will allow us to bring down the 2x like we normally would do here. But then after that, natural log of e is equal to 1. So this basically just goes away, and we get 2x is equal to the natural log of 5/2. Now to solve for x here, you could do a couple of different things. I'm just going to multiply both sides by 1/2. The other option is you could divide by 2. But in this case, I'm going to multiply by 1/2, and my final answer here is going to be 1/2 natural log of 5/2. Or if you had used 2.5, you might have 1/2 natural log of 2.5. So another possible way that you could write this answer would be like this. And of course, if you did that, you could also even write it like this. So all of these are correct. I just personally like this answer the best. Then, of course, you could plug that into a calculator and get a decimal approximation, but I'll skip that here. In this next example, we're going to solve the exponential equation algebraically and then graphically. So first, let's do it algebraically. So here we have e to the 3 minus 2x is equal to 4. Now, once again, first thing we want to do is isolate the exponential expression, which it already is. And then I'm going to take a logarithm of both sides. But again, I don't want to use log base 10. I want to use natural log. So we have natural log of e to the 3 minus 2x equals natural log of 4. Now, in the last example, I brought down the exponent and then I canceled natural log of e. You can actually take away the natural log of e right away because this is one of our properties of logarithms. So if I do that, we get 3 minus 2x equals the natural log of 4. Now from here to solve for x, I am going to move my 2x to the other side and I'm going to bring the natural log of 4 over here. So we have our 3. We're going to subtract natural log of 4 to the left side. And we're going to add 2x to the right side. And the reason I'm doing this is because now I just have to divide by positive 2. And so x is going to be 3 minus the natural log of 4 divided by positive 2. And then we'll go ahead and plug this into a calculator just to get a decimal approximation. And so you should practice with your calculator as I do this, but I get 0.8069. That's the approximate answer for the solution to this equation. Now, how would we solve this graphically? To do this graphically, I would like to consider f of x to be equal to e to the 3 minus 2x, and g of x to equal 4. And the basic idea is that if I graph two functions f of x and g of x, let's say, we can solve for where they're equal to each other by finding the point of intersection. So this is the basic idea here. So we're going to graph g of x equals 4, which is very simple. That's just a flat line, right? And then we're going to graph e to the 3 minus 2x, which is going to be some kind of a decreasing exponential function. So let me go ahead and bring in that graph. And so you can see here is the graph of g of x equals 4, and here is the graph of e to the 3 minus 2x. And we can see that they intersect here, and that happens at an x value that is very close to that value right there. And that does appear to be approximately 0.8069. But the nice thing about graphing calculators is that we can actually touch the screen here and it will tell us the approximate solution. So let me show you what that looks like. And so now you can see, indeed, they do intersect at a value of x, which is 0.80685, which is this number. And the y value, of course, is 4 there, but we only care about the x value. So even when even when equations are difficult to solve algebraically, we can use graphing calculators to help us solve these things. Next, we look at kind of a special example. We want to solve the equation e to the 2x minus e to the x minus 6 equals 0. And this is classified as an exponential equation of quadratic type. And the basic principle here that you need to know is that e to the 2x is the same as e to the x quantity squared. So if I rewrite this equation, I can write it as e to the x quantity squared minus e to the x minus 6 is equal to 0. And I'm only putting parentheses here for effect. But from this point, we could make a substitution. We could let u equal e to the x. And if we do that, this becomes u squared minus u minus 6 equals 0. And this is very easily solved using factoring. And we can see that the solutions are u equals 3 or u equals negative 2. Now, of course, we're not solving for u in this problem. U is something that we made up to make the problem look more simple for us. So when I'm done solving for u, I need to remember that u is really e to the x. And so I'm going to rewrite this as e to the x equals 3 and e to the x equals negative 2. Now to solve these, you can take a natural log of both sides. And this, of course, is going to give us x equals the natural log of 3. So there's one solution. And on the other one, when you take the natural log of both sides, you have a problem here because the natural log of negative 2 is not real. So there's no solution that you get from here. So the only solution is the natural log of 3. In our next example, we have sort of a random example of an equation involving exponential functions. So this isn't of a particular type. You just have some exponential functions mixed in with some polynomial type functions. And so how would you go about solving something like this? Well, we know that when something is equal to 0, we can often use factoring to help us solve it. So notice that these two terms have a common factor of e to the x and also a common factor of x. So I can factor this as x e to the x multiplied by 3 plus x equals 0. So just double check to make sure that that factoring makes sense to you. But then from here, we would set x e to the x equals 0 and 3 plus x equals 0. Now, of course, in the second equation, x is just going to be negative 3. That one's pretty easy to solve. But in the first equation, we have a product here. And the only way a product can equal 0 is if the first factor equals 0 or the second factor equals 0. So one answer here is going to be x equals 0. And the second part of this has no solution because e to the x, the exponential function, is never equal to 0, right? It never touches the x-axis. So we have two solutions here, 0 and -3. Now let's switch over to solving logarithmic equations. So in this particular example, notice that we have a bunch of logs in this equation. One important thing to point out is that they are all log base 10. So what I can do in this particular case on the right-hand side is I can combine these logarithms into a single logarithm. Because we're adding these logs together, we're going to multiply x minus 3 and x plus 3. Now from here, the only way log base 10 of one thing can be equal to log base 10 of another thing is if these two things are equal. So we talked about this previously, but what I can do is just drop the logs here. And that gives us x squared plus 1 is equal to x minus 2 times x plus 3. From here, we'll go ahead and multiply out the right-hand side. And then now from here, we can subtract x squared from both sides. And that's going to give us 1 equals x minus 6. And then solving for x here, we get x equals 7. Anytime you're solving a log equation, you need to consider if you put this number back in, does it make sense? And what you're really looking for here is making sure that you're not taking the log of a negative number or the log of 0. So notice when I plug in 7 here to any one of these three, I do not get log of a negative number and I do not get log of 0. So 7 should be the correct answer. Now we have some general guidelines for solving logarithmic equations, and you could read these here, but basically you want to isolate the log term on one side of the equation if you can. Then write the equation in exponential form, if you can, and then solve for the variable. So let's take a look at this next example. So here in the first part, I want to solve for natural log of x is equal to 8, and I want to solve for x here. So what we're going to do here is just remember that natural log means a log base e. So I can rewrite this as log base e of x is equal to 8. And now we know from the definition of a logarithm, we can say e to the 8 power is equal to x, right? That's the definition of a logarithm. And what do you know? We've solved for x. X must be e to the 8. For the second part, we have log base 2 of 25 minus x is equal to 3. And very much in the same spirit, I can change this by taking 2 and raising it to the third power and setting that equal to 25 minus x. So 2 to the third equals 25 minus x. 2 to the third is 8. And then from here, I can add x to the left side, and I can subtract 8 from the right side, and I end up getting x is equal to 17. In our next example, we have 4 plus 3 times the log of the quantity 2x is equal to 16. So here what I want to do first is isolate the logarithm if I can. So I'm just going to subtract 4 from both sides. And that is going to give us 3 log of 2x is equal to 12. Now I can further get the log by itself by dividing by 3 here. So if we divide both sides by 3, we're going to have log of 2x is equal to 4. And now we keep in mind that log here means log base 10, and then we can change this into exponential form. So we can say 10 to the 4th power is equal to 2x, and that means 10,000 equals 2x, so x must be equal to 5,000. In the next example, this is very similar to the first one, except that notice there is no log on the right-hand side. So we've got log of x plus 2 plus log of x minus 1 is equal to 1. So first thing I'm going to do is combine these logarithms. I can do this by using multiplication, so log of x plus 2 times x minus 1 equals 1. And now that I have a single logarithm, we can just use the definition of a logarithm to write this in exponential form. So we can say 10 to the 1st power is equal to x plus 2 times x minus 1. And then simplifying here, we get 10 equals x squared plus x minus 2. And then from there, we'll subtract 10 from both sides, just a standard quadratic equation at this point. And we can use factoring to help us finish here. And we're going to get two answers, -4 or +3. Now keep in mind, when you're solving log equations, you cannot take the log of a negative number. You also cannot take the log of 0. So if I plug -4 in here for x, notice that we're going to get a negative number there. So -4 is not one of our solutions. Now if you plug in +3, everything's fine. So we only have one solution in this problem, x is equal to 3. Now for more complicated equations, again, sometimes we need to lean on using graphing to help us solve. So in this particular problem, if you try to solve this algebraically, it's going to be pretty much impossible. So what I'm going to do to solve this graphically, once again, is I'm going to think of graphing the function f of x equals x squared, and graphing the function g of x equals 2 times the natural log of x plus 2. And then we'll search for the point of intersection. And you'll notice when you graph these two functions, x squared is here, and 2 natural log of x plus 2 is here, you'll see that you get 2 points of intersection. So one of the solutions is x is approximately equal to this one, which is 1.6007, and the other solution is x is approximately equal to -0.7117. So we have two possible solutions here. And do take note of the fact that if you plug in a negative number here, when you add 2 to that number, it will be a positive number. So both of these solutions are valid. In the next example, we have an equation that deals with transparency of a lake or a body of water. So if I naught and I denote the intensity of light before and after going through a material, and x is the distance in feet the light travels in the material, then according to the Beer-Lambert law, which is this equation here, where k is a constant depending on the type of material, you can figure out the intensity of the light left over after traveling through x feet of water. So the first thing we want to do here is just solve this equation for I. So to solve for I, notice that the I is inside of this logarithm here. So first thing I'm going to do is get rid of this -k, and I can do that by multiplying both sides of the equation by -k. Now after doing that, we're going to have the natural log of I over I naught is equal to -k times x. Next thing I'm going to do is just remember that this is base e here, and we can rewrite this without using a logarithm. We can write this as e to the -kx is equal to I divided by I naught. And then to solve for I naught, we're just going to multiply both sides here by I naught. That will cancel this out. And we get I equals I naught e to the -k times x. So this is the first part of the problem. For the second part, it says that for a certain lake, k is equal to 0.025, and the light intensity, the initial light intensity, is 14 lumens. Find the light intensity at a depth of 20 feet. So this means if you shine a light into this water and the brightness is 14 lumens, what is the brightness going to be after going through 20 feet of water? So all we have to do for this is plug everything in. The intensity I is going to be I naught, that's the original intensity, which is 14. So 14 multiplied by e to the power -k, which is -0.025 times x, and in this case, x is 20 because it's 20 feet. And so all we have to do is plug this into a calculator, and then we'll get the result. And when doing that, you get approximately 8.5. So the brightness of this light after going through 20 feet of water is 8.5 lumens, whereas it started as 14 lumens. In the next example, we want to find the term for an investment to double. So a sum of $5,000 is invested at an interest rate of 5% per year. Find the time required for the money to double if the interest is compounded according to the following: semi-annually for the first part and continuously for the second part. So let's focus on semi-annually. We do have a formula, A equals P times 1 plus R divided by N to the NT. In this case, we know the amount of money in the future is going to be double, so that's $10,000. We are starting with an initial principal balance of $5,000. The interest rate is 5%, which is 0.05. And the number of compoundings is 2 because it's semi-annually. And we want to solve for t. So we're going to plug everything in here. 10,000 is equal to 5,000 times 1 plus 0.05 divided by 2 to the power 2 times t. Now, if you divide both sides by 5,000, you'll see on the left-hand side, you just get 2. And that 2 just represents doubling, right? Because if you're talking about doubling, this amount of money is always going to be twice as much as this amount of money. Next, we can do a little simplifying here. 0.05 divided by 2 is 0.025. And then when you add that to 1, you get 1.025. And then that's raised to the 2t power. Now to solve for t, I'm going to take the natural log of both sides. I like using the natural log. This is going to allow us to bring the 2t down in front. So we have the natural log of 2 equals 2t times the natural log of 1.025. And now to solve for t, I'm just going to divide both sides by 2. And I'm going to divide both sides by natural log of 1.025. And that's going to cancel these out and cancel these out. And we end up getting t is equal to the natural log of 2 divided by 2 times the natural log of 1.025. And then we'll just plug this into a calculator to approximate. And you can see here that we get approximately 14.0 years. So it's going to take about 14 years for your money to double under these circumstances. Now let's take a look at how long it would take if it was compounded continuously. So in this case, we have a different formula. When you're compounding continuously, the amount of money that you will have in the future is equal to P times E to the RT. Again, in this case, A is $10,000. That's the amount we want to have in the future. P is the amount we're starting with, which is $5,000. And the interest rate, again, is 5%. But in this case, there is no N. So we're just going to plug everything in here. We get 10,000 equals 5,000 e to the 0.05 times t. We'll divide both sides by 5,000 just like we did before. That's going to cancel this out and give us 2 on the left-hand side and then e to the 0.05 t. Next, we'll take a natural log of the left side and a natural log of the right side. On the right-hand side, these are going to cancel, leaving us with natural log of 2 equals 0.05 times t. And the final step here is we just divide by 0.05. And so t is equal to the natural log of 2 divided by 0.05, which we can approximate on a calculator. And you can see here that the value is approximately 13.9 years. So not a lot of difference, right? So when you compounded semi-annually, remember it took 14 years. If you compound continuously, it takes 13.9 years. So there's not a lot of difference between compounding continuously and compounding semi-annually. And in our final example, we want to solve for the time required to grow an investment. So let's suppose a sum of $1,000 is invested at an interest rate of 4% per year. Find the time required for the amount to grow to $4,000 if interest is compounded continuously. All right, so once again, we know that our formula here is A equals P e to the RT. The amount of money we wish to have in the future is $4,000. The amount of money we have in the beginning is $1,000, and then e to the 0.04 times t. So we're just solving for t once again. I'm going to divide both sides by 1,000, and that's going to give us 4 equals e to the 0.04 times t. Next, we'll take a natural log of both sides. And on the right-hand side, that's going to cancel out, giving us natural log of 4 is equal to 0.04 times t. And then finally, we'll just divide both sides by 0.04. And that gives us t is equal to natural log of 4 divided by 0.04. And again, we can just plug this into a calculator to approximate. And you can see in this case, this takes about 34.7 years. So it's a lot longer, even though the interest rate is only a little bit less. But the main reason it's so much longer is because $4,000 is 4 times the amount of our original investment. So this is like doubling your money twice, right? So that's why it takes so long for this to happen. And that concludes this video lesson.